welcome to the video tutorial for chapter 7.3.2, interference. So our first learning objective is to describe the interference pattern produced by a double slit on a screen, including the modulation effect produced by a single slit. So that is, first off, it's over here in this particular section right here. So this is learning objective number 1 right here. So some comparisons, first off, to single slit is, I'm going to exaggerate this a little bit. So we noticed that that was not very nice. Okay, so let's see if we do a better job of that. So the center is a little bit higher. And so what we're seeing that is it sort of has an oval or egg-like shape or football, rugby ball-like shape, where in the very center, it's much brighter in comparison as it leads out to the points of destructive interference right there. And so there's another destructive interference right there. And so you can see that the double slit interference also follows exactly where the single slit minimas are there as well. Okay, so they follow exactly on the same lines. But what we also have is that each of these guys, actually I'm going to use the green color for this. So for the double slit, we also see the presence of our interference pattern. So we're seeing maximums and minimums within the single slit maximums and minimums as well. Okay, so there is sort of like two interference patterns that are happening here right now. Okay, the idea of modulation, so I like to think of the modulation effect as that the single slit is sort of controlling or enveloping the double slit interference pattern, right? So the single slit diffraction pattern will sort of control in some ways the double slit, right? So sort of overpower. So even if the double slit was to have a maximum there, the single slit sort of overwrites that and says, nope, we're destroying all of the interference that's going on there. So that's the idea of modulation. Our second learning objective is very similar to our first one, but it's looking at it in terms of a graph type format. So sketch and interpret the intensity graph produced by the double slit. So that's actually the part in red in between here. So the double slit intensity pattern that is graphed looks like the following thing. And you can see what it physically looks like down here as well. So this is the physical manifestation of that. And here we have the graphical representation of that, okay? So again, you sort of notice the idea of modulation here very, very clearly from the single slit, okay? Is that it'll control, or that the double slit will only go up to the maximums where the single slit is also coming down on that particular part of the curve as well. Okay, again, you just need to sketch and be able to interpret that information there. Nothing too major. We'll have another activity to pull some information off of that in terms of the angle theta. So we'll get to that when we look at, I think it's question number 3. So lastly, we want to distinguish between the width and the separation of the slit and their effects on the intensity. So they sound very, very similar, but the width has to do with single slit. And again, I'm going to use the color blue to represent that along with the graph. So hopefully that's making some connections in your brain. And the separation of the slit is the double slit. Okay, so there's two different variables there for two different formulas. but they're both sort of working together in the same experiment, as we can see. So first off, the slit width can be for the single slit and for the double slit. But here we can see both slits are being adjusted in terms of size. Sorry, that's over here on the left-hand side. So this is the slit width. Okay, and the other one is the separation. And the separation is for the double slit, and this is for the single slit. Here we have our two formulas. So I'm going to highlight the two things here in the formulas as well. So again, I'm going to use the color to help match us up. This is single. This is double. And we have two very similar variables as well. Sorry, I didn't keep to my promise of using red for the double slit. So this is double, and this is single. Okay, so the letter B here, this is the slit width. Okay, and so if you're referencing that, it's the width of the slit, as you can see there. Right, that little measurement right there. Okay, the other one is little d, is the separation of the slit, as you can see there, and we have a really wide separation there. And what we're looking at is the effects on the intensity pattern. So what that's really affecting is the slit width is having a direct effect on the angle, and D, for our particular purposes, S will have an effect on the interference pattern. So let's look at this. Let's look at this right here. So here we have our double slit. Okay, so here we have the interference pattern for the double slit experiment itself. And there is sort of an enveloping or modulation effect from the single slit, which I'm using in blue as well. So when we modify the value of D, which is the separation, so according to this formula, if we decrease D, then S is going to increase. In other words, they're inversely proportional to each other. So what that means is, so I'm going to assume we have sort of like a smaller d here. I'm going to do sort of a big D. Okay, I don't have much room there. So if we had a big D, so I'm going to do a massive separation here in comparison. Okay, so let's say this is double the amount here. So that's D. And so S is going to, so D is going up here. So we have an increase in D. Therefore, S must go down. And so what's going on here is this particular distance here is going to shrink. That's the separation, okay? So we're going to get something much more compressed, sort of like that. Okay, and if we were to have actual values, if this was, let's say, 2 centimeters, this might have shrunk down to 1 centimeter. Okay, and likewise, if this was maybe 1 centimeter, this is maybe increased to 2 centimeters. Okay, so increase in D will decrease S. Okay, so that affects how close the destructive interference is there. Now, interestingly speaking, if this whole distance for our single slit, let's say this was, I don't know, 15 centimeters, that actually still holds true for this other interference pattern. So, right, I'm just going to kind of do it like this. Oh, kind of don't have enough room there. Okay, so it will still hold for the entire 15 centimeters. Okay, changing D will not have any effect on that. Now, to look at the opposite situation here, so I'm going to actually just move down here. Okay, I've got way too many different things there. So if we're looking at our other formula, this is the single slit formula, lambda over B. So remember, B was the width. Now, we normally look at, we can look at this in terms of the, actually, I'm going to do, so I'm going to do a really thin one. So we have our interference pattern here. And let's say we have a thicker, let's do a massive one. So we'll do something that's like really obvious. So the separation in between is not changing, right? This separation, S, is not changing, but the value of B is changing. And so what is that going to do on our pattern? So we can see here, B and theta have an inverse relationship. So let's say we have our original pattern here. So suppose we have something like this. Okay, we're just going to look at the center maximum. And of course, so we'll have some interference stuff from the double slit there as well. So try to stick with 5. So B is decreasing. The angle of theta is increasing. Now, to really understand what this angle theta increasing really is it's looking at it's looking at this particular angle right here. That particular angle. Okay, so it's the angle from the center, the absolute center, to the first destructive interference. Okay, and it's only looking at sort of half of that entire pattern itself. I'll go back up to, if you're curious about the trigonometry for that, we can look at that, okay? But that's exactly what we're looking at, and it's looking at that particular angle. Okay, so if B is going down, then the angle is going to increase. Then that's going to mean that the angle on this side has to be even bigger than this one. Okay, so this is 30 degrees. I'm just going to do something really drastic here. We probably have like a 60-degree angle here. Okay, again, I'm just exaggerating just so you can really sort of get the idea. So that's going to create a much bigger interference. Sorry, not interference. It's going to spread out the where the destructive interference pattern is. Okay, so I'm going to use that blue color as well. So again, if this is the center, it's going to drop off here. Okay, and so what that might mean, okay, that's obviously going to continue to over to the other side as well. So again, we might have, this doesn't really change. Okay, so the separation between the double slit interference will still remain the same. Okay, so if the distance between the center of this maximum and the center of this maximum was 2 centimeters, then the distance between this and this, now it might not be quite according to scale, but that would also, in theory, also be 2 centimeters. Okay, each and every one of these would also be 2 centimeters. Okay, now of course we only have we sort of have like 2.5 constructive interferences in here until it reaches that point of destructive interference marked by the single slit interference, okay? So now we've sort of got, I'm going to sort of refer to these as peaks, okay? So we have like one peak here, we have two peaks here, we have three, we got four, we got five peaks here instead, okay? So the single slit is holding more of these peaks or intensity peaks, okay? Whereas we have one, two, and we have maybe three here, okay? So that is the differences that we're going to have on, as we mentioned, the width and the separation. Okay, so lastly, we're gonna we'll look at some examples to really show and illustrate that and see what that really looks like. Okay, so example number 2. So let's do some calculations and figure some things out. The graph shows the intensity in arbitrary units, not SI units, of diffraction patterns produced by coherent monochromatic light on a double slit. The wavelength of the light is 510 nanometers. So we've got the wavelength. So I'm going to write that down first. Wavelength is 510 nanometers. Okay. We have an angle, and remember the angle is measured in radians here. So angle theta is 0.1 radians. And we want to figure out the slit width. Okay, so that's pretty straightforward. Is angle theta wavelength over the slit width. Okay, rearrange the formula. Okay, and as I mentioned, okay, these are the steps you want to take when you're actually doing your exam. So start practicing this. Identify the formula. Rearrange the formula. Then do your substitution. Okay, IB loves seeing these step-by-step type stuff, okay? So 510 nanometers, that's 10 to the power of negative 9 meters. So I'm going to make the conversion, I'm not going to write nano. And then we have 0.1 radians. Okay, so B, I'm going to grab my calculator. So 5.1 divided by 0.1 radians. So that's going to give me 5.1 times 10 to the power of negative 6 meters. Okay, now this is question A. Now question B is an interesting question because we're asked to calculate the separation of the slits. So the separation of the slits normally comes from Young's double slit formula here. This one, okay? It's asking us to calculate this value, which we don't know. And we don't have any of this other information except for the wavelength. So how do we actually get this, okay, without figuring out capital D and little d? Well, there is actually a little trick here. And the trick is to figure out, the information is actually within here. So if you recall, that little distance right there, okay, the distance between one of these maximums, or what I called peaks earlier, okay, that distance is a separation, the value of S. Now, the way to actually solve this is we need to figure this out in radians, and we can actually solve it reusing this formula for B. Okay, so what we're going to do is we're going to supply the angle here. So I'm going to count how many peaks there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and it looks like there's 10. Okay, so there's 10 peaks, or I guess we can mark this as 0, and that would be our 10th peak right there. Okay, so 0, 1, 2, 3, okay, and then that's 10. So there's 10 peaks, which means the angle for each of the red, peaks is 0.1, right? It's 0.1 divided by 10, right? So that is 0.01 radians. Okay, so what we need to do then is, it's the same thing. We're just going to do our substitution. So the wavelength hasn't changed. It's still 510 times 10 to the power of negative 9 meters. The radians has changed, 0.01 radians. And actually, if you look at that, this is just shifting the decimal place over by 1. So it's even, it's going to be one value larger than, so it's going to be 5.1 times 10 to the negative 5. Yeah, I think it's one larger. It's definitely a shift of only one decimal place. So let me just verify this on my calculator. Divided by, yeah, it gets larger, yeah. Okay, so 5.1 times 10 to the negative 5 as opposed to negative 6. Okay, so this just happens to be what this particular question is, okay? Similarly, let's say there was, if the double slit interference pattern had changed, so let's say there were only 5 peaks. So again, I'm just sort of imagining that there were only, let's say, 5 peaks along the way. So again, this sort of goes down, goes up, goes down, up, down, up, down, and up, let's say. Okay, so let's say there's 5 peaks. So what you would do is then that would be 0.1 if this was the graph. Divide that by 5, right? Okay, so that would be your value in radians. So 0.05 instead. Okay, and then you make your division. Okay, let me know if that was a little bit too confusing. I can do a separate video for that. Okay, example number 3. This is interesting because the color of the light will actually affect both patterns, the single slit and the double slit interference pattern. And the reasoning for that is if you, let me just see if I can find that big chunk a little bit earlier. So I'm just going to steal this, copy. So the reasoning is, I'm just going to move that over here. Okay, let me clean this up a little bit. Okay, if you look at both equations, I don't know why you erased double. Both of them actually have a shared variable, which is lambda, or the wavelength of the light. Okay, therefore, a change of the wavelength, in fact, an increase, oh sorry, no, what we have here is, let's see here. So when the incident light is changed from red to blue. So from red to blue, I'm purposely using a different color here. So if you recall our visible light spectrum, we have red on one side and we have violet on the other side. Okay, so I'm going all the way down the spectrum because blue is essentially pretty close to violet already. Blue would be about there, right? You got green, you have like yellow. So we're sliding, I'm purposely changing the question a little bit to slide all the way down the spectrum. And so a decrease, so if we look over here, this was red, right? If the wavelength decreased, so we're going from red to blue, then equally, the angle also has to decrease. The slit width also has to decrease as well. And so, again, what that really means is I've kind of drawn the patterns of what that actually looks like here for you in a rough scale, okay? So red light is the furthest apart. Green light is getting narrower. Red light is even more narrow, okay? Now, within that, you might also have like a single slit, like what you see right here, okay? And the green would be a little bit smaller than that. So I'm going to try to draw this a little bit more narrow, like right around there, like that. Okay, but this would also kind of, the green would also, the double slit interference would also squeeze within here as well. Okay, because the slit separation is also changing. Okay, so if they're changing in proportion to each other. So big the big value there, and this is only measured. This is measured in half of the amount as radians. Okay, so as the angle shortens. Okay, so again, let's say this is 1 radian, right? This would be 2 radians. Okay, and so suppose also the single slit here. If this was maybe 2 centimeters here, this would also shrink here as well. So this would also be 1 centimeter, okay? So they're both shrinking because, as we said earlier, the wavelength is duplicated in both, okay? But what we saw earlier was that if we changed the slit width or we changed the slit separation, changing the separation will not have an impact on that. Likewise, the width will not impact that. Okay. Otherwise, these variables would have been in both of the other formulas as well. Okay. So that's example number 3 explained, and that is the end of the tutorial for chapter 9.3.2. Hope you guys got all of that. If you didn't, I totally get it. This is there's a lot of information, very challenging. Let me know if you maybe need a follow-up video on this unit. Okay, thank you guys. See you guys next time.